To determine the appropriate wire size for a meter bank, an electrical contractor typically follows several steps. Firstly, the total load must be calculated. This is done by multiplying the amperage rating of each disc by the number of discs. In this case, with 4 100 amps discs, the total load is 100 amps times 4, equaling 400 amps. Secondly, determining the demand load is essential. The demand load is the actual load expected to be drawn from the meter bank. For remodeling projects, utility companies or city building inspectors often provide guidelines or calculations to determine the demand load based on the building type and its intended use. For example, let's assume a demand load of 50%. Thirdly, the current carrying capacity must be determined. The current carrying capacity of a wire is determined by its cross-sectional area and the material used. For copper wire, the current carrying capacity can be found in tables from the National Electrical Code. Fourthly, select the appropriate wire size. The wire size must be large enough to handle the demand load. The electrical contractor will typically select a wire size that is at least equal to or slightly larger than the calculated current carrying capacity. Assuming the calculated current carrying capacity is close to 300 amps, a 2/0 wire might be suitable, but this needs to be verified with code requirements. Fifthly, and very importantly, verify with code requirements. The electrical contractor must also ensure that the selected wire size meets the requirements of the NEC and any local building codes. A 2/0 wire is a common choice for meter banks with 400 amps total load and a 50% demand load, but always confirm code compliance. Several additional factors also come into play. Consider the distance from the meter bank to the main lug panels. Consider any voltage drop considerations, as excessive voltage drop can impact performance and efficiency. Consider the type of insulation and conduit used, as these factors affect the wire's ampacity rating. Electrical contractors typically determine the correct wire size for a meter bank by calculating the total load, estimating the demand load, and selecting a wire size that meets the current carrying capacity and code requirements. Utility companies and city building inspectors may provide assistance with demand load calculations for remodeling projects. The National Electrical Code, or NEC, provides tables that specify the allowable ampacities of insulated conductors. Ampacity is the current, in amps, that a conductor can carry continuously under the conditions of use without exceeding its temperature rating. These ampacity ratings are based on specific conditions, including the conductor material, insulation type, insulation method, and ambient temperature. NEC Table 310.15b16, formerly Table 310.16, is a crucial resource for determining the ampacity of conductors. This table provides ampacity values for various conductor sizes, insulation types, and temperature ratings when installed in raceways or cables or directly buried in earth. The ampacity values in this table are based on an ambient temperature of 30 degrees Celsius or 86 degrees Fahrenheit. If the ambient temperature is higher than 30 degrees Celsius or 86 degrees Fahrenheit, correction factors must be applied to reduce the allowable ampacity. Correction factors are found in NEC Table 310.15 Barno Table 310.15b2 depending on the insulation type. The NEC also provides adjustment factors for situations where multiple current-carrying conductors are bundled together in a raceway or cable. When conductors are bundled, the heat generated by each conductor can raise the overall temperature inside the raceway, reducing the ampacity of each conductor. Adjustment factors are found in NEC Table 310.15 Cone. These adjustment factors reduce the allowable ampacity based on the number of current-carrying conductors in the raceway. To correctly size conductors, it's essential to account for voltage drop, which is the reduction in voltage that occurs as current flows through a conductor. Excessive voltage drop can cause equipment to malfunction, reduce efficiency, and potentially damage equipment. NEC Section 215.2a provides guidelines for voltage drop in feeder conductors, recommending that voltage drop should not exceed 3% for feeders and 5% for the combined feeder and branch circuit. To calculate voltage drop, several factors must be considered, including the conductor length, conductor size, conductor material, current, and power factor. The voltage drop can be calculated using formulas such as the following: voltage drop equals 2 times K times I times D divided by circular mils, where K is the direct current constant, approximately 12.9 ohms for copper and 21.2 ohms for aluminum. I is the current in amps, D is the one-way distance in feet, and circular mils is the cross-sectional area of the conductor. After calculating the voltage drop, it's important to ensure that the voltage at the load end is within acceptable limits. If the voltage drop is excessive, a larger conductor size may be required to reduce the voltage drop to an acceptable level. In addition to ampacity and voltage drop, several other factors must be considered when selecting conductors. These factors include the type of insulation, the location of the installation, and the environmental conditions. The insulation type must be suitable for the voltage and temperature requirements of the installation. Common insulation types include THHN, THHW, and XHHW. The location of the installation can also affect the conductor's selection. For example, conductors installed in wet locations must be suitable for wet locations. Conductors installed in direct sunlight must be sunlight resistant. Environmental conditions such as temperature, humidity, and corrosive substances can also affect conductor selection. Conductors must be suitable for the specific environmental conditions of the installation. In summary, determining the correct wire size for a meter bank involves several steps, including calculating the total load, determining the demand load, selecting the appropriate wire size based on ampacity and voltage drop, and verifying compliance with the NEC and local building codes. Additional factors such as conductor insulation, installation location, and environmental conditions must also be considered. Always consult the NEC and local building codes for specific requirements and guidelines. Understanding conductor ampacity is vital for electrical safety and system performance. The NEC provides detailed tables and guidelines for determining the allowable ampacity of conductors based on various factors. By following these guidelines and considering all relevant factors, electrical contractors can ensure that conductors are properly sized for the intended application, preventing overheating, insulation damage, and potential fire hazards. Voltage drop is another critical consideration when sizing electrical conductors. Excessive voltage drop can lead to equipment malfunction, reduced efficiency, and potential damage to equipment. The NEC provides guidelines for limiting voltage drop in feeder and branch circuit conductors. By calculating voltage drop and ensuring that it remains within acceptable limits, electrical contractors can ensure that equipment receives the proper voltage for optimal performance. The National Electrical Code, or NEC, is a comprehensive set of standards and guidelines for electrical installations in the United States. It is published by the National Fire Protection Association, or NFPA, and is updated every 3 years. The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. The NEC is not a law itself, but it is often adopted by state and local jurisdictions as part of their building codes. Compliance with the NEC is essential for ensuring electrical safety and preventing electrical hazards. The NEC contains numerous tables that provide essential information for electrical installations. These tables cover a wide range of topics, including conductor ampacity, conduit fill, box fill, and grounding electrode sizing. NEC tables are based on extensive research and testing and are essential for ensuring that electrical installations are safe and compliant. Some key NEC tables include Table 310.15b16, which provides ampacity ratings for conductors, Table 310.15 cone, which provides adjustment factors for multiple conductors in a raceway, Table 250.122, which provides minimum equipment grounding conductor sizes, and Table 430.52, which provides maximum overcurrent protection settings for motor circuits. To effectively use NEC tables, it's essential to understand the table headings, footnotes, and any associated notes. It's also important to use the correct table for the specific application and to consider all relevant factors that may affect the table values. The NEC is a complex and comprehensive document, and it's essential for electrical professionals to have a thorough understanding of its requirements. Continuous education and training are crucial for staying up to date with the latest changes and interpretations of the NEC. The National Electrical Code, or NEC, is organized into chapters, articles, and sections. Each chapter covers a broad topic, such as wiring methods, overcurrent protection, or grounding. Articles provide more specific requirements within each chapter, and sections provide detailed rules and guidelines. Chapter 1 of the NEC covers general requirements, including definitions, rules for electrical installations, and requirements for electrical plans and specifications. Chapter 2 covers wiring and protection, including requirements for conductors, overcurrent protection devices, and grounding. Chapter 3 covers wiring methods and materials, including requirements for raceways, cables, and boxes. Chapter 4 covers equipment for general use, including requirements for appliances, motors, and transformers. Chapter 5 covers special occupancies, including requirements for hazardous locations, healthcare facilities, and agricultural buildings. Chapter 6 covers special equipment, including requirements for electric signs, electric welders, and electric vehicles. Chapter 7 covers special conditions, including requirements for emergency systems, fire alarm systems, and communications systems. Chapter 8 covers communications systems, including requirements for telephone systems, data communication systems, and cable television systems. Chapter 9 contains tables and examples that supplement the requirements in the other chapters. To navigate the NEC effectively, it's essential to understand the organization of the code and to be familiar with the key chapters and articles. It's also helpful to use the index and table of contents to locate specific requirements. The NEC is a constantly evolving document, and it's essential for electrical professionals to stay up to date with the latest changes and interpretations. Continuous education and training are crucial for ensuring compliance with the NEC and maintaining electrical safety. In addition to the NEC, electrical installations are also subject to local building codes and regulations. These codes and regulations may vary from jurisdiction to jurisdiction and may impose additional requirements beyond those specified in the NEC. It's essential for electrical contractors to be familiar with the local building codes and regulations in areas where they work. Local building codes often address specific issues that are relevant to the local environment, such as seismic requirements, wind load requirements, and floodplain requirements. They may also include requirements for energy efficiency, accessibility, and fire safety. To ensure compliance with local building codes, electrical contractors should consult with local building officials and obtain the necessary permits and inspections. They should also maintain accurate records of all electrical work and be prepared to provide documentation to building officials upon request. Compliance with local building codes is essential for ensuring the safety and integrity of electrical installations and for protecting the public. Electrical contractors play a critical role in ensuring the safety of electrical installations. They are responsible for designing, installing, and maintaining electrical systems in accordance with the NEC and local building codes. To perform their duties effectively, electrical contractors must have a thorough understanding of electrical theory, wiring methods, and safety practices. They must also be able to read and interpret electrical plans and specifications. Electrical contractors must also be skilled in the use of electrical testing equipment, such as multimeters, clamp-on ammeters, and insulation testers. They must be able to use this equipment to troubleshoot electrical problems and verify the safety of electrical installations. Electrical contractors must also be committed to continuing education and training. The electrical industry is constantly evolving, and it's essential for electrical contractors to stay up to date with the latest changes in technology and regulations. Electrical contractors who are committed to safety and professionalism are essential for protecting the public from electrical hazards. Remember that this information is for educational purposes only and should not be considered a substitute for professional engineering advice. Always consult with a qualified electrical engineer or licensed electrical contractor for specific design and installation requirements.